to introduce Ty. It's my honor and privilege to introduce him to you. So Ty Garibay is Vice President of Engineering for Embedded Processing at Altera Corporation. So previously, Ty was the Director of IC Engineering for the OMAP division in the wireless business unit of Texas Instruments, and was responsible for the development of TI's OMAP mobile application processor from architecture specification to production silicon. So in the distant past, he was almost 20 years designing microprocessors of many kinds, including low-power ARMs, MIPS, and high-performance x86s, MIPS, 68Ks, and 88Ks. So a whole range of CISC and RISC machines in there, right? Ty holds over 30 patents in the areas of computer architecture, circuit design, design methodology, and design for test. And Ty received his BSEE and BA foreign languages from Southern Methodist University in 1986. So Ty, we welcome you to the podium, and give him a hand.
Thank you, John. And thank you, Hans, for arranging to have me here. I really appreciate it. Pretty much the intro just reminds me that I'm old, but I guess that translates to experienced. The only thing I would recommend for next year's speaker schedule is that nobody schedule a speech on the opening night of Monday Night Football. I got fantasy players playing right now, man. Anybody got a score? Oakland? No? Nobody? What a bunch of nerds. Come on. Whip out an iPhone already. Yeah, it's the football with your hands. It's the one, yeah, backwards, I understand. So anyway, I wanted to talk some about Altera's vision of what we call silicon convergence. So first or eventually we'll talk about what it means, and talk about how to bring together different levels of programmability to create a system solution. I'll do the compulsory intro to Altera, some look back, look where we are now, and then look forward. For those who don't know, Altera is just around the corner, about a mile away. Relatively mature company by Silicon Valley standards. The first reprogrammable logic semiconductors, and reasonably good size these days. And as they say, a leading supplier of FPGAs, CPLDs, and even ASICs on a good day. Lots of offices around the world. My office is in Austin, Texas, so I'm just here visiting. But we have 1,000 people up the road, and I've got about 60 in Austin. We sell a lot of stuff to a lot of markets. So we do make a lot of money. That's one of the good things about Altera. Trust me, this is a lot better than working for a company that don't make money. What is a PLD? Who knows what a PLD is? Hey, he's been around. He's got hair that looks like mine, though. So there's a lot of different kinds. We separate them out into CPLDs and FPGAs. I don't really see much of a difference. Really, you can think of them as size, the number of gates for the most part.
Isn't it basically the graining of the logic?
Yes. Yes. So you have usually much larger arrays of things than what we call an FPGA, but it's all programmable, unless it's an ASIC or an ASSP, which is not. So what's the good part about it? You can change it in the fields. So most of our customers are driven by a desire to be able to either fix bugs, respond to changes in the environment over the length of the time that a product may be in production or installed, and not have to go roll a truck, pull a board, whatever it is, and still be able to address the issue. We are a technology leader, of course, isn't everyone? In our case, it's true. Named the top 100 most innovative companies. We're actually number 100. But hey, we made the 100. You know, yeah, I was actually pretty happy about that. first to 40 nanometer with our FPGAs, first to 28. So we are typically a technology leader relative to silicon process technology. So it's a fun place to be in terms of working with very advanced technologies across the board. What are the differences between these things? CPLDs, we can go fast to market. The total cost of ownership is low because they're small. FPGAs can be programmed very easily, software or hardware. Again, the total cost of ownership, we'd like to say low, but it is volume dependent. ASICs, you can only program through software, assuming you have a programmable element in your ASIC. And the time to market can be relatively fast if you're working with Altera, because we can bring a hardened version of your FPGA very quickly to market. If you're working on developing your own ASIC from scratch, the cost can be very high, very slow time to market, and you have very little flexibility in terms of responding to changes in your environment. I like the footnote, which is that if an ASSP is available and you didn't design it, then you're already late. Right? So somebody else has already got a product to market in your market, so now you're competing on cost or something else. So that's an intro to Altera. What I wanted to talk a little about is looking back at history. Actually, I wasn't expecting as many experienced individuals in the crowd. Sir?
Is your hard copy growing as a percentage?
Yes. As a percentage of designs, less so. So the designs that have been done over the last 5 years are coming to maturity and are proliferating.
You might want to repeat the question.
Sorry? Okay. The question was, is the hard copy business that we have continuing to grow and as a percentage of total sales? And the answer is yes. And we foresee that'll be the case for a couple more years. And then, in fact, I may mention what we see as the next step there. As I was saying, I didn't expect to see quite so many experienced individuals in the crowd, so this may not be quite as interesting as I hoped it would be. So those who don't know history are doomed to repeat it. I had to look that one up to get the right structure there by Edmund Burke. So who remembers this? All right, there's a couple, all right. So it's a 387. It was a standalone floating point unit for an Intel 386 processor. And then very shortly thereafter, there was that one, and that one, which I helped build and profited off of for a while. So there was a market that was built around the fact that you could add functionality to an Intel processor, be it a 386 or a 486. Go ahead.
Actually, I don't like to lecture and correct you something, but 487 had the x86 integer input. It was a 46DX equivalent. So it's not a purely a full processor.
480. The 487.
387.
No, the 487 was a coprocessor.
No, you actually put it alongside another 46SX with disabled SS.
Okay. I understand what you're saying. So the technology, yes, I agree with you. The technology worked that way. The effective market was that you added a second chip and you added floating point functionality. What's interesting is that you're able to build a business around certainly what Intel never intended to be a business. And there became a variety of these things available. Waitex were actually very interesting. They were good products. They added a lot of value to image processing back then. But then integration happened. Right? After this point in time, floating point became a de facto standard in the x86, and there was never again a standalone floating point accelerator. So over time, we see similar examples in the growth of the OMAP family that I was a part of over the last 10, 15 years. When we started this family, a little bit before my time, it was really just an ARM and a DSP and some peripherals. Advanced for its time, but if we look at where it went, in the second generation, 2420, we added graphics and imaging, enhanced the other elements of the design, bringing it up with each generation, adding much higher performance graphics and a full 720p video processor, until we have the current generation that's on sale today in a Droid Razor, Kindle Fire, whatever. It has multiple ARM cores, super high-end graphics, a 2D graphics processor. By nature, life is like a box of chocolates, and you never know what you're going to get. So everything you build has to be reasonably flexible. The integration is kind of a standard way of life in our industry, right? We shrink, we add, we shrink, we add. But as we add things, you have a tendency to potentially become more and more market specific. To work against that, you have to put in programmability to guarantee that the product ends up being flexible enough to meet enough market demand to be viable as a product. Over time, the process allows us to add more at reasonable cost and lower power, or similar or lower power, at least until we got to 28, and then 20 nanometer, that may not be true anymore, but it's been true for a while. In the case of OMAP, what we saw is that each of those elements that were added over time were in and of themselves programmable. So we could handle a reasonably wide variety of things while adding functionality to the product. So we have integration, flexibility, and then over time, standardization drives volumes. So you have systems from different vendors, TI, NVIDIA, Cortina, STMicro. If you close your eyes a little bit and look at these things, they're all pretty much the same. They have the same fundamental blocks, and there's a reason for that. As markets mature, the solutions tend to standardize and become interchangeable because the customer base is demanding that. The set of requirements that make a viable product have been defined by the market, and now the end system customers want to see that set of capabilities. They want to see it from multiple vendors. They want to play the multiple vendors off. It happened for railroads. There used to be all the different versions of gauges in the world. Now there's still two, I think. But yeah, and automobiles, interchangeable parts, definitions of how things should work, and PCs, of course, there's really very little diversity left in that ecosystem. Good and bad sides. It gives pricing power to the customer. So as a market standardizes, people in that designing products in that market cede power to their customers effectively. Tends to inhibit innovation. Very little is going to change drastically in a standards-driven market. Again, we see it with the PC that they aren't going to change. You're going to add a tablet. It's a theoretically different thing. But what it does do is it allows markets to ramp exponentially in volume, typically. So once you get to the standardization phase, costs are driven out, you get mass adoption. Okay, so that's a good thing. It's just a different thing. So between integration, flexibility, and standardization, we have natural trends over time for most markets. If you don't like change, you're going to like irrelevance even less. I thought that was funny. Eric Shinseki is a pretty sharp general. And any solution that is not sufficiently integrated, flexible, and standard may effectively become irrelevant over time. And there's nothing worse than being irrelevant in our industry. It's a sure way to go out of business very, very quickly. So what does that mean to where we are today? In the current landscape of things, there's a pretty wide range of IC options. You can go everywhere from a standard microprocessor or DSP. FPGAs have some combinations of capabilities for those things in soft and hard logic. And then you can go to an ASSP, which is market targeted, but still perhaps generic enough to use in different applications, or a full custom ASIC. Each of these can be programmed somewhat with software, and then some of these, the FPGA can be programmed in hardware itself. The need for IP speed and efficiency, the ability to change your design to respond to changing constraints, pushes people to use more and more higher performance solutions. The need to get greater ROI means that you want to have more flexible solutions. You want to be able to serve more markets with the same piece of silicon. Of course, being from Altera, we believe that some combination of programmable logic yields perhaps the best possible solution where we're able to hit very high performance with the products that can take advantage of the fine-grained parallelism of the programmable fabric, but the ability to be flexible enough to get ROI across multiple designs.
So I was wondering, your segmentation is a GPU and ISSP?
Yes. The question is a GPU and ASSP, and it is actually an ASSP to start. If you think about it, it's actually something that's currently being integrated, and shortly will go the way of one of my beloved companies, SGI, where you had a very nice ecosystem of high-end graphics computers that was eaten away from below and eventually came to naught. We see that today very clearly, where the market segments that are ripe for standalone video cards are becoming smaller and smaller. You have high-end gaming and medical imaging pretty much at this point. Most everybody else is okay with an integrated Intel or ATI graphics. Good? Sutherland? I have not seen that, but let me talk to you afterwards about this. I'd like to learn more. Thank you. Now I'm intrigued. Let me try to get back on track here. Over time, over the different families of Altera, the percentage of, I heard that, the percentage of the die which is dedicated to purely programmable functions has actually dropped significantly. Why? Because in order to continue to increase the performance of the solution for our customers, we have added more and more hard logic with programmable logic around it, and even the hard logic itself is often very configurable. But there's DSP blocks, floating point units, there's big chunks of RAM, there's full data paths in there that the coarse tools, the synthesis tools that we have, can map onto and create optimal solutions for any given input of RTL. So over time, we're seeing that purple bar grow and grow. So the IP content is going up, but it's still highly programmable. It's still flexible enough to be a generic solution for our customers. Although at Stratix, at the Stratix level for high performance, you have a lot more DSPs in the mix. Why? Well, because for that product line, you want to see, or we sell mostly to high-end telecom and networking. They want to do a lot more DSPs. At the low end, low cost, there's less need for DSPs. We turn that some percentage of that real estate into just more gates, which in control applications you tend to use more of. at the low end. So we're flexible. We have different mixes at different product families, but the trend is clear. The mix of hard logic and soft logic is a better solution and becoming a better solution over time. Also a better solution is the mix of processors and programmable logic. So this is a metric that we take from our customer interactions that shows what percentage of our customers' designs used processors historically, and then going forward, projecting what we believe will happen. And this is based purely on our own proprietary Neos embedded soft processor. So it doesn't even take into account the forward-looking addition of ARM processors to our product line, which I'll talk about in a minute. So since the creation of Neos at the beginning of the millennium, we've seen a very steady increase in use, and we've tried to work with that and give more and more tools to help our customers use the processor. And it makes sense. We're growing, we're adding more and more gates to our larger chips as time goes on. And there's I believe, being a CPU guy, there's a natural limit to the number of gates you're going to have before you want a processor that outside those gates that controls them. And I think you can see that we kind of hit that point in 4 or 5, and we really haven't looked back since, as the gate densities continue to increase and the needs for control processors continue to increase as well. Go ahead.
So I used to work at Altera, so I understand how the company works to some degree. But based on that, if I understand it correctly, Altera has a feature called TalkBack, which allows...
Sorry.
It's called TalkBack, something like that, that allows Altera to get anonymous information about the usage of which IPs.
I have never heard of that. I've only been with the company for a year, so it could be.
Yeah. So I was wondering, what is the correlation between this source, because we use like Dart, but I was curious about how this correlates with the Altera's proprietary information they got from customers, because from my understanding, they know exactly who's using which IPs.
I sure hope so, but we'll just go with this data. The question is this data consistent with what we see reported by our users? And I have to say I don't know. I'll go with this. So FPGAs over time have gone from pretty much logic elements and RAM to transceivers, high-speed SerDes, hard memory interfaces, DSP blocks, and now in the most recent generation adding microprocessors, the Cortex A9 from ARM. So we've evolved very well beyond the logic fabric. The SoC FPGA, which is my product, my team's product, is a combination of the technology from ARM and our leading edge technology in 28 nanometer for our Cyclone and Aria families. System-wise, not very complex. We have a there it is. We need a higher power one than this on. The ARM cores in the top with an L2 cache. We have USB, Ethernet, I2C, SPI, QSPI, NAND, flash, timers, DMA, a bunch of GPIOs, all that kind of stuff. The fundamentals of an embedded system. All of this is built into a hard macro, which we put onto a FPGA die with very high bandwidth interfaces at the FPGA to SoC boundary, both directions. So we're able to get far more bandwidth between the programmable fabric and the processor system on die than you could ever get with standard designs today, where they're PCI, whatever. So the potential for new solutions being able to be developed with this approach is very high. Even off chip, we have very good bandwidth because you can have the SerDes up to 10, 12.5, I think, gigahertz, and we also have a hard memory, a hard controller for memory DRAM in the SoC itself, and a separate one for the FPGA. So you could have a split memory system with extremely high bandwidth for the overall product.
Is the DSP a hard core or a soft core? I see you have it listed in the FPGA.
It is a data path. So it is a hard macro data path, and they're sprinkled throughout the programmable fabric, and there's logic put next to them that is intended to become the control for that data path, but it's fully synthesizable. And we have a tool called DSP Builder, which takes Simulink input, so you just spec out your system in Simulink, and it puts together a system of adders, multipliers, shifters, whatever is necessary, creates the interconnect between those and the control for the data path to implement the function. So that's the kind of productivity enhancements that we already have in place to allow people to create very complex systems very quickly. So high-level block diagram, again, not too different than what you expect from any other SoC. Processor, L2 cache, big, huge, hairy interconnect, and I/O, low-speed peripherals, higher bandwidth peripherals, and then the interfaces to the FPGA and the SDRAM controller. The Cortex-A9 is a reasonably good processor. It's certainly the sweet spot of today's consumer electronics products. It's your iPhone 4. It's almost every current phone out there at the higher end. So very high volume, very efficient, both power and area efficient. So we feel like this is a pretty good processor to build the platform on. Offers both a single and double precision floating point and the Neon media processing instruction set for byte SIMD type applications. It allows for true coherency within the two cores. And then we also have what we call I/O coherency between any master in the FPGA and the ARM cores L1 and L2 caches. So a master in the FPGA can request data of memory. It'll go past the ARM memory system. If the ARM is holding that data, it'll respond. The converse isn't true. The ARMs are not coherent back into the FPGA. That would have been too hard. But so you have some assistance there where you don't have to completely manage all of the coherency in software. Just copying data back and forth all the time. The FPGA itself is our most efficient to date, both from a power and area point of view on the Cyclone side. Then on the ARIA side, we have a mid-range product that's very well suited for applications like remote radio head, for base stations, what else? Some imaging applications. So it's got a much larger availability of programmable gates. We have very high bandwidth from the peripherals, from the memory controllers, both inside and outside of the SoC, PCI, and straight up SerDes that can be programmed to be different protocols. And then all of our memory blocks are ECC protected. So for reasonably high reliability systems, we can protect the data. So as you'd expect me to say, the best of all worlds. We bring together the processor, the ability to add IP into the programmable logic. We have DSP blocks, and then pure FPGA for control blocks. But in the end, you need more than silicon to make a product. We have a collaboration with a number of vendors whose processors that we purvey. We also have a tool called QSYS for building up systems. We have a wide array of IP that can be added into the programmable fabric. And we continue to innovate in terms of tools that allow our customers to build more complex systems more quickly. We'll try to touch on some of those if we have time. On the development side, bringing the ARM processor on chip creates an interesting challenge in that we have to have now a tool set that can generate binary code for the ARM along with the tool set that we have today called coarse to generate programming for the logic gates. So this half of the system is a standard FPGA flow. This half is essentially a standard ARM flow as we try to bring together all the tools necessary to allow our customers to take advantage of both types of programmability in our product. Luckily, with ARM comes a significant ecosystem of tools and applications. So we're counting on some of that being there from the overall ecosystem. But for our own purposes, we are creating Linux, VxWorks, OSC, and microC ports for our parts, and then helping to deliver a full solution as an SDK to our customers. We have created a virtual target model. That's just a software model of our system that would allow someone to start software development today. Right, Eve? Today, right? It's ready to go? Yeah, he's not saying anything. Yeah, it's ready to go. So start software development today and very easily port to Silicon when it goes to full production. Longer term, the answer lies in raising the level of abstraction. What have we always done every time we've gotten to where systems have been too complex? I was lucky enough to experience the transition from schematics to synthesis. Years ago, synthesis, I guess, to IP, last 10 years. And each time we've tried to bring the level of abstraction up. Until very recently, FPGAs were pretty much stuck at the RTL level. What we've tried to do over time is to create tool offerings that help our customers create systems in our FPGA more efficiently. SOPC Builder was the first one. The current iteration of that is called QSys, and it's a graphical system creation environment where you can instantiate IP of your own creation or from our library, create an interconnect for it, and our tool flow will put that into the front end of Quartus. So you're able to at least get one level above the RTL, even above the IP, creating the full system. But in the future, we have to do better. So the only way of discovering the limits of what's possible is to venture a little way past them into the impossible. Gotta love Arthur C. Clarke, one of my favorite authors. As I mentioned, the big challenge on any algorithm in an FPGA is that you're essentially designing hardware. It's often difficult to design. I guess that's why some of us still have a job. Verifying code, especially something to code something that's scalable across different FPGAs, across different members of different product lines and costs of FPGAs. Generally, software programmers have some difficulty using FPGAs as multi-cores to accelerate parallelizable applications because it's difficult to address the resources in the system. So there's a need for a programming model that allows the designer to think about the FPGA as a fully configurable multi-core. Programmers would prefer that everything looked like a software environment. They want to start with C, typically with a sequential program, and then add parallel APIs. They want instantaneous feedback and a rich debugger. And the ideal environment would allow for a standard multi-core programming model rather than being tied to some kind of FPGA architecture. It would abstract away lots of the details of the hardware, but still be efficient enough that you're not paying an inordinate amount for taking advantage of that abstraction, and allow for that quick feedback time that software programmers would like to have. So that's the big idea behind OpenCL.
We don't look at higher level languages. There's languages like Clojure now that provide built-in multi-thread capabilities that support these kinds of things. C is not being used
You know,
in the hardware community.
I would tend to agree. Yeah. So the question is, are we looking at true high-level languages? I think what we have going on in FPGA side of the industry is something of a burn me once, burn me twice. The FPGA companies have tried on multiple occasions to bring the level of programming, data entry, system entry up, and have gotten very little traction, almost no return. The programming community is highly fractured over what is the best way to do anything at a higher level. And so we've found that it's very difficult to pick any winner in that space yet. And it's been the technology of tomorrow since, I don't know, probably 98, 97 or earlier. So what we're looking at today is a practical solution to real problems. I would love to be able to leverage that into yet a true higher level language of which, an OpenCL program was one module, and you could bring it all together with different ways of coding. And I think that long term, hopefully that will happen. But right now, what we see is that because of the GPU model, and the investment that the NVIDIA and ATI are putting into that, and even Intel, there is a growing community of OpenCL programmers that are learning how to create solutions with OpenCL mapping onto GPUs. What we see in our space is that taking those same solutions and mapping them onto FPGA can be far higher performance and far lower power. So right now, we see there's a tool out there that people are willing to use, and we'd like to take advantage of it. Go ahead.
What is your status of your OpenCL implementation? And the reason I'm asking for this is because I was at Altera about a year ago, and I did warn their number 2, number 3 executive in a meeting that, your company has hardly anybody who understands PC architecture at the company, and you're trying to do OpenCL and trying to compete with NVIDIA or AMD. And isn't that crazy? That's the question, and basically there's not much response coming from it. So based on that, how well does the OpenCL-based product that you're touting works? Because I kind of have a lot of skepticism about that.
That's fair. So to be clear, not touting any product today, talking about a technology that we believe is going to be very useful for the future of programming FPGAs. Altera has announced that we are investing in OpenCL and that we will have a product that will be generally available for use next year. We are making significant investments in adding resources, experienced folks to help us make that product real. There's no doubt in my mind that this is a step that we are going to make that will improve the ability of our customers to design at a higher level and create products more quickly. Is it the last step? No. Is it going to be perfect? Probably not. But it'll be better than what we got now.
Yeah, well, the reason I'm asking is because I got snubbed by them last year, so I passed up.
Let's keep it to the questions, okay?
So in the end, what do you want to do with OpenCL? You basically want to make the parallelism explicit so that you can take advantage of it across a variable number of processing elements. In the OpenCL programming model, you have a host thread and kernels. So right today, of course, with existing FPGAs, the host is running on whatever x86 processor in the system. The x86 is communicating generally over PCI with an FPGA, farming threads out to the kernel processors that are synthesized into the FPGA fabric. We have all the same challenges that anybody else would have: memory bandwidth, floating point. We have a few floating point cores sprinkled throughout the Stratix FPGA, and then trying to make sure that we are keeping the system busy as possible. The host program is generally written in standard C, and it communicates with the accelerator device through a set of library routines. You start up a kernel, move the data over to the processing elements, execute the kernel, tear down the kernel, bringing the data back to the host processor. This is a compute model which was, of course, created by graphics processors. That's the only way they have to access memory. Longer term, of course, you saw your next speaker, the HSA guy, will probably talk about the future of OpenCL from the HSA point of view, which includes the creation of kernel-to-kernel pipes so that you can have chained functionality a la Cray in the future. And I think once we get that into the specification, the true power of an FPGA will really be unleashed to be able to have multiple processors of varying types active in the fabric simultaneously, and then chaining data from one to the next. We'll get rid of that bandwidth limitation that's really throttling the available performance today. Okay. Will future FPGAs have virtual memory such that they can communicate across boundaries of designs? Understood. Mm-hmm. So, right. So HSA is actually proposing a solution to that, and so you'll see that next month. And the onboard ARM processor is available to channel the data as necessary between the synthesized processing elements without ever having to leave the FPGA to go back to the external host. So some of that will be available through the hardware, but I think the rest of it has to come from improvements in the way the software is specified. Go ahead. Fair. Mm-hmm. Yeah. So the question is, what do we do with PHYs? And then once you are in the business of accelerating kernels, what does that do to the architecture choices of the FPGAs themselves? Is that right? So the PHYs are an interesting problem, right? Because they come with unmapped data, raw data. So far, and again, we're at the very beginning of this, especially thinking about how an integrated SoC FPGA would work in this environment. But at least right now, the PHYs tend to be used to bring the data in, move the data to a processor, and then it bounces back and forth, and then it goes out the other PHY. So you're not typically going to bring data from a PHY directly into a kernel. It doesn't have a name. Now, again, with the pipe mechanism of HSA, it is theoretically possible to name pipes. So you could probably put a small processor on bringing the data and formatting it in off the pipe, off the SerDes, filling an input buffer, and then have that be the beginning of an HSA pipe into a chain of processing elements. I don't know enough about the underlying software to know whether that's possible. Clearly, it's got to be a goal for us, where this is one area where we're very different from the graphics guys.
So kernel refers to the control to the data path. The data path is fixed.
No, so a kernel in this context, what is a kernel? A kernel in this context is just a program that contains both control and data, and it's synthesized onto the programmable fabric.
Oh, so in real
install the kernel, you run the operation,
Mhm.
you install the new kernel.
You can do that, and so by taking advantage of what we call partial reconfiguration, you could tile functions in and out based on a demand-driven or a least recently used type of an algorithm, and that's really kind of an exciting possibility that we're looking at with our tools. Is how can we combine some of these features like partial reconfiguration, like OpenCL kernels, to where you can essentially page in a function, use it, page it out, page in another function. That's independent of how kernels work, though. In the current systems that we're seeing today, the kernel mapping is static. It's doing that function. You just do that function a lot. If you want to change that function, you load another program into the FPGA, and you're doing now another function. Go ahead, Amitabh.
So a lot of the memory management that's implicit in OpenCL, just like Abdullah, is about managing context in local memory to the transfers of the and then managing how much is being shared memory and what is shared host and shared local clusters. What does that mean in the context of you which have probably RAM?
It actually maps very well to an FPGA. Oh, sorry. Okay. It maps very well to an FPGA because of the inherent dual-ported nature of all of our RAMs. So you allocate a RAM to a function, but they also serve very well as read-write buffers, fill in read empty buffers. So you compile OpenCL to the FPGA, kernel programs run on the FPGA, the host is whatever process you have in the system, and each of the kernels becomes a set of pipeline functions that you can now essentially multi-thread in a pipeline fashion. So any sufficiently advanced technology is indistinguishable from magic. We'd like to be able to do magic sometime soon. This is a step, bringing together QSys functionality that we have today, bringing together DSP Builder, bringing together OpenCL, bringing together true high-level language synthesis are the ways to go in the future. So that we have. Okay. So we have, to enable convergence, we have to have effective integration. I think we're on that path. Bringing together true programmable logic, standard cell functions, the ability to turn products into smaller, lower-cost ASIC solutions, application-specific IP for vertical markets. We have DSPs, we have microprocessors, we have analog, we have memory. So we have a true full-chip system. By definition, all of our systems are extremely flexible, both with hardware and software programmability, such that one piece of silicon can meet the needs of many applications. So you can get to the point where you can get the ROI you need to justify that product, hopefully. And longer term, we need to essentially create mass innovation for developers. What does that mean? We need to move forward on a broad front with building on the tool suite we have, but then adding more to dramatically increase the productivity for system developers, not just software developers, system developers, where the system is one view of the system is the software, but the underlying hardware architecture also needs to be specified. And we need to facilitate transitions across the hardware-software boundaries to allow for power, performance, cost optimizations semi-transparently. Now, this has been a goal in our industry for decades. I'm sure it will continue to be a goal for a while. But I think we're on the right track to being able to facilitate this better than any other solution I've seen in almost 30 years in the industry. So I'm pretty excited about it, and hopefully you guys can follow along, buy a few, play with them. We'll have something out at a nice Beagle board cost point in the not too distant future where you can learn and play with it yourself. So.
You're welcome. And to cap it
All
off,
right.
I
I don't have one of these yet.
exactly. This is custom made. So thank you very much.
Thank you.
And
Thank you
again,
very
we,
much.